Hello and welcome to the online course on optical communications. In the previous module we were discussing the modes of an optical fiber. We started with 4-step process. We looked at the Maxwell's equation, expressed the transverse components ER, E phi, HR and H phi in terms of the longitudinal components EZ and HZ. Then we solved the Helmholtz or the wave equation for EZ and HZ and found solutions corresponding to the core region as well as solutions corresponding to the cladding region. In core we have seen that the solutions are of the form of Bessel functions of the order nu and first kind, whereas in the cladding you have Bessel functions of the second kind and order nu. Right. So, this is what we have done at the previous module, where we had stopped at that point where we had to apply the boundary condition in order to evaluate the arbitrary constants. So, once you evaluate the arbitrary constants, then you can go back and find out ER, E phi, HR and H phi, because you have already obtained EZ and HZ. So, we will now continue the discussion of modes in an optical fiber, and this is just a simple summary of what we had done, which I just described to you. We know that ER and E phi, HR and H phi are functions of EZ and HZ, and in core we see that EZ as a function of R will be Bessel function of the order nu. Nu is an integer in this case. U and W are positive constants which are related to the k vector and the propagation constant vector beta, as we have discussed in the previous module. Nu again is the order, and with respect to phi it goes as e to the power j nu phi, right. It simply tells you what is the angular distribution of the modes is. So, if nu is equal to 0, then the fields are independent of phi. If nu is equal to 1, then the functional dependence on phi is like cos phi and sin phi. Similarly, you will have cos 2 phi, sin 2 phi, indicating the kind of angular rotations or angular wave numbers. With respect to z, you have e to the power minus j beta z. This is the propagating solution that we are considering inside the fiber. Therefore, in the fiber you want oscillatory modes with respect to R, an angular distribution that is determined by e to the power j nu phi, as well as propagating terms in the z direction, which is e to the power minus j beta z. There is a constant A which is multiplying this electric field. Similarly, the equation for Hz will also be exactly in the same form as the equation for Ez, and the solution would be then of the same form, except that it may have a different arbitrary constant beta, right, or sorry, arbitrary constant B. The reason why B is not the same as A should be obvious, because if you take del cross E, then that del cross E must give you H, and in the process of taking del cross E there will be additional constants which would come into this equation. Because of that, you have a different constant B which is taken here. In the cladding region, of course, Ez is equal to some constant C times the Bessel function of the second kind, right. These are the exponentially decaying Bessel functions, as we have discussed in the previous module. And boundary conditions, what it does is to stitch the oscillatory behavior in the core to the decaying solutions in the cladding. So, if the core mode starts, for example, if the core mode is Bessel function J0, then it is maximum at R equal to 0, and then as R starts to increase, the Bessel function keeps on reducing. So, let us say at some constant R equal to A, you stop this process. Okay. So, you have a Bessel function which is nicely decaying like this. At some point you stop this one. Okay. This of course would correspond to the actual core radius, but you can consider this to be any arbitrary point. Now, at this point the field will have a certain amplitude Ez, because it is starting from some peak value at R equal to 0, and it would have dropped to a certain value, because this is a J0 function which we are considering, the Bessel function of the 0th order. So, it would drop and it would reach a particular point. Okay. So, let us say some value here which is Ez at R equal to A. Now, Maxwell's equation tells me that the field must be continuous at this point, because the tangential electric field across two dielectrics must be continuous across that particular boundary. Therefore, at this point if Ez has dropped and it has become Ez1, then the new field must take off from that point and decay as the radial distance increases. So, you have to just adjust the amplitudes of the decaying constant as well as the amplitude of the J0 or J1, J2, depending on what mode solution that you are looking for. Okay. So, that is essentially what the boundary condition does to you. This is of course pictorially, but what you actually are going to do is to set up a set of equations which tell you that Ez1, which is the electric field in the core region at R equal to A, which is the core and the cladding interface, must be equal to Ez2 at R equal to A. So, inside the core, assuming that we are looking at J0 type of a solution, this is how you would start. It would be at certain peak value and then it would start to drop like this, and at R equal to A it would have reached this point. Next, what this condition implies is that the decaying part of the solution must begin at the same point and then it has to decay out like this. Okay. And of course, the modes are symmetric on both sides, so which means that the modes are going along for R less than A as such, or rather R in the other way around as well. And again you have to stitch the solution here and then let the mode go to, let the mode basically get decayed. Suppose you reduce the core radius, then what happens? Well, then the stitching has to start at this point, right, because the field would stop at here for Ez1. So, Ez2 must begin at the same point and then go in this decaying fashion. So, this is what the boundary condition is basically doing, is just basically evaluating what is the amplitude of this one, what is the amplitude of here, and how to adjust these amplitudes such that I am able to evaluate, I am able to satisfy the boundary condition as well as evaluate the arbitrary constants. Similar to the continuity of the tangential electric field components, there is also continuity of the tangential magnetic field components. So, your Hz1 must also be continuous at the same boundary. Okay. For the R equal to A interface, Hz is also a tangential component of the magnetic field, so that must be continuous. You also get two additional constraints. One is that E phi 1, which is the angular component of the electric field at R equal to A, that must also be equal to E phi 2, which is the angular component of the electric field at R equal to A. So, you can imagine, you take this cylindrical cross section like this and you look at the cross section here R equal to A, you see that Ez will be something that is coming out like this, correct. So, to this boundary, this Ez is actually a tangential component, right. To the same boundary, this fellow, the one which is going like this, which would be the angular component E phi, this would also be tangential. However, the radial component would be coming out of the surface like this, right. So, if you imagine this is a circular cross section, the radial component would be coming out like this. So, for this curve at R equal to A, which separates the core and the cladding, this radial component is the normal component, and that is not the constraint that I want to apply. So, for R equal to A in the cylindrical coordinate system, Ez and E phi are the tangential components. For the electric field, Hz and H phi are the tangential components for magnetic field. So, the last one is that H phi 1 must be equal to H phi 2. So, you can take a look at this small exercise which will allow you to express E phi as well as H phi in terms of Ez, the longitudinal component Ez and Hz. So, if you have solved this exercise in the previous module, which I had recommended you to do so, you would then be able to use the values of Ez, Hz given in these two equations for the core and the cladding and obtain the expressions for E phi and H phi. So, I am assuming that you will take this exercise seriously and do this one, okay. And once you have done that, you will actually develop 4 equations, okay. You have 4 unknowns which are A, B, C and D, and there would be 4 equations coming in from Ez. A and B are the amplitudes of the electric and magnetic field Z components, C and D are the electric and magnetic field components E phi and H phi. So, you get 4 equations, 4 unknowns. The easiest way to solve this one is to write down a matrix, right. So, you have the 4 unknowns written out as A, B, C and D. Let me extend the matrix here, and then there will be a 4 cross 4 matrix over here, which then should be equal to 0. That is the solution of the linear equation, linear simultaneous equations. Now, if you want all non-zero values of A, B, C, D, right, in general you want non-zero values of A, B, C, D. The trivial solution would be that, well, you set A, B, C and D all equal to 0. In that case there are no modes, there is no problem. I mean, you might be tempted to do that, but you won't learn anything from optical fibers if you do really that one. So rather than that, what you have to do is that to make A, B, C, D in general non-zero, this matrix, whatever that matrix that I have obtained by applying the boundary condition, this determinant of this matrix must be equal to 0. So if I do that, and this again I can warn you that it is not very nice thing to do it because it takes a lot of time. It is not difficult, but it is just that it is very tedious. Okay. So it will take a lot of time, but if you really put pen and paper together and then spend some time, you will be able to find that determinant, and the solution of that equation, determinant of the matrix equal to 0, which I am not going to write the matrix here, you can refer to the textbook for the entries of the matrix. Okay. The solutions turn out to be J V K nu, sorry, these are not V, these are nu, times K1 square J nu plus K2 square K nu must be equal to beta nu by A whole square 1 by U square plus 1 by W square to the power 2. Okay. So you see that this is the solution where of course J nu is actually given by another complicated expression, J nu prime of U A divided by J nu of U A. There is also a U that is getting multiplied. K nu is given by K nu prime, which is a derivative of the Bessel function with respect to the argument. So K nu prime W A divided by W into K nu times W A. And similarly here J nu is this one and K nu is this one. So you can substitute all this and then try to solve this equation. A simple warning, this is going to be very difficult, you will not be able to solve this analytically, you will have to resort to some numerical technique to solve this problem. Okay. To obtain the roots of this equation, which will tell you what the value for beta is, remember the goal here is to actually get beta. Okay. And you can't simply say, oh, beta nu by A square is equal to this quantity, I can take it into the denominator and then take the square root of the whole thing. It does not work that way, because this fellow U contains beta implicitly, W contains beta implicitly, there is a U which contains beta, this one also contains beta, this is also beta, this is also implicitly containing beta, correct, because what is U square? U square is nothing but K1 square minus beta square. So there is beta there also. So these equations are not the simple equations that you would be able to solve it, these are quite complicated ones. So the suggestion is that you do not really have to do it analytically, it is quite impossible, whereas you can use some numerical method to solve for the equations. And in the assignment problem we will walk you through the solution of this equation using a numerical technique, which you can program using a language such as MATLAB. Okay. So for now just take that fact that this is the equation that you have to solve in order to obtain beta. Okay. Now there is one parameter which is sitting here, the parameter that is sitting here which is not specified is this order nu. Am I free to choose this order nu? Turns out that yes, I can choose the order nu, and nu starts from 0, 1, 2, 3 and so on. Okay. If you choose nu equal to 0, what happens to the right hand side of this expression, the root equation that we are writing? The right hand side will simply disappear, because it is getting multiplied by beta nu by A whole square and nu is 0, so this entire right hand side goes away. Then you have two solutions, right, two possible solutions. One is that this term which I am denoting as 1 be equal to 0, or this second term 2 be equal to 0. It turns out that if 1 is equal to 0, that is J nu plus K nu is equal to 0, then this corresponds to solutions of the form TE 0M. Okay. And this of course will happen only when nu is equal to 0, therefore the solution actually has to be J0 plus K0 equal to 0, and you can then use some recurrence relationship which relates J0 of x, J1 of x, okay. Similarly K0 of x and K1 of x, the Bessel functions of the first and second kind. You can use some recurrence relationships for the Bessel functions in order to solve this equation, or rather write down this equation in a slightly easier form to solve. that would turn out to be J1 UA divided by U J0 of UA plus the K0 term is K1 WA divided by W K0 W times A. So, this entire thing must be equal to 0. Normally what happens is that if you already have a fiber A, the radius gets determined already, right. So, and K1 square, because in U K1 square also gets determined because it is the property of the material, the unknown factor is still beta, but beta you will be able to obtain by solving this equation, right. So, you can solve this equation to obtain solve for beta given all the other parameters. Now, you might wonder a little bit here, well, I have U and W also, what do I do about that, right. You can actually relate U square and W square. It turns out that if you take U square plus W square, because U square is nothing but K1 square minus beta square and beta square minus K2 square, the sum of U square and W square is nothing but K1 square minus K2 square. Now, you can solve this equation and write W square is equal to K1 square minus K2 square minus U square, and then say W is equal to square root of this entire thing. So, you have K1 square K2 square minus U square. So, you can put this W into this expression, thereby eliminating the requirement of having two variables U and W. Okay. So, you can put all these things into one. So, this equation that you are looking for, which is the equation that tells you the value of beta, will now have only U term sitting inside, and when you solve this equation you are going to get a solution for U, but U and beta are related. So, once you find U, from this you find beta. Okay. It is like find U and then find beta. So, this is what you would have to do, and when you do that you end up with what is called as a TE0M modes. Okay. Now, suppose this is not the term that is 0, suppose the second term is equal to 0, which implies that you go to that equation K1 square J0 plus K2 square K0 must be equal to 0. Again you can use some recurrence relationship. So, you have K1 square J0, this is the script J0 plus K2 square K0 is equal to 0. So, these are not the Bessel functions, these are those expressions for script J0 and script K0 that we have written. Okay. So, when you take this term equal to 0, the solutions that turn out to be are called TM0M. I will just explain to you what the meaning behind this TE0M and TM0M. When you take term 1 equal to 0, I said that the modes are TE0M. It means that the electric field component Ez actually vanishes, Hz will be non-zero, and depending on the other this one, all the other components are present. Okay. Now, look at what is happening. Ez is 0, which means there is no component along the fiber axis. All the electric field that is there will be in the form of Er and E phi, and they are in the plane that is perpendicular to the z axis. So, this is the z axis, this is the plane that is perpendicular to it. Because Ez is 0, the electric field lies in the plane that is perpendicular to the axis of propagation. So, this perpendicular to the axis of propagation means that the electric field is transverse to the direction of propagation, and because of that we call this as TE0M mode. 0 stands for the way in which it would be behaving in terms of radial direction, that is radially how the mode would spread out or how would it would behave, and M stands for how it would change azimuthally, along angularly how would it change. If M is also 0, then it would change, well, it has no dependence on phi, and unluckily or luckily for us there is no such mode as TE00 mode. So, M has to be equal to 1 at least in order to get the first mode. Okay. So, you get TE01 mode, similarly you get TM01 mode. Now, the meaning of TM should be very clear to you. When I consider the same z directed propagation, Hz is 0, so the magnetic field will lie entirely in the plane that is perpendicular to the z axis, Hr and H phi. Okay. So, this is Hr and this is H phi. So, this is called as a transverse magnetic mode. Similar to TE01, the lowest order mode that can propagate is TM01. So, what do we mean by lowest order values? The lowest order propagation means that for a given value of nu and m, there exists a certain non-zero field pattern. If you take TE00, then there is no pattern for that, and therefore such a wave will not exist at all. Okay. Then what is this pattern? Pattern is basically the dependence on r and dependence on phi. It is a plane that is perpendicular to the axis, and in that plane if you for example take nu equal to 0, then the fields would decay like this. They would have a maximum value at the center, but then they would decay in this fashion, right, in a like a Bessel function. However, if you consider nu equal to 1, then the solutions will be of the form J1. In that case J1, you know that r equal to 0 starts off at 0 itself and then it goes up like that. So at the center of the fiber the field will be equal to 0. So these are the different types of modes that you are going to get. We have seen TE0M, TM0M. The corresponding equation, I will leave this as a simple exercise for you to write down, because I have already written down what is J0. So this is basically J0 and this is K0. Okay. So from J0 and K0 you can substitute that. K1 square, you know, K0 square N1 square, K2 square is K0 square N2 square, substitute and then get this equation. Okay. Again you can make this substitution for W. You can express W in terms of U, find U, then find beta. Okay. That is how you would find the value of beta. Okay. So this was TM0M. In general, for nu that is not equal to 0, you unfortunately end up with two types of waves called as EH waves and HE waves. EH waves means that E is greater than H, that is Ez amplitude is greater than Hz amplitude. Ez amplitude, remember, was A in the core, Hz amplitude was B in the core. So A by B, if this is much larger than 1, then we call this as the hybrid EH mode, okay, or we sometimes call as electric hybrid mode. Similarly, HE mode will occur when Ez is less than Hz mode. Okay. So you get A by B much less than 1. So this is called as hybrid electric mode, electric hybrid mode and hybrid electric mode. Okay. So it's the confusion wise a little bit, because you know it's the hybrid mode notations are little confusing. These are the old terminology, but unfortunately they are stuck with us. Okay. If you look at what happens to the situation, let us consider this situation. Suppose I have radius A fixed, I have the numerical aperture of the area, I mean of the fiber fixed, which means that I have fixed up N1, I have fixed up N2, in turn I have fixed up K1, I have fixed up K2. Okay. Suppose I consider one lambda, let us say this lambda is 1300 nanometer. Okay. And I consider what happens as lambda starts to increase or lambda starts to decrease. Lambda decreasing means frequency is increasing, lambda increasing means frequency is decreasing. You can go both ways. Okay. In any way you take, whether it is increasing or decreasing, as you change lambda, something else changes, right. Lambda is related to K0, which is the free space wavelength, and K1 is given by K0 times N1. I have fixed N1. As I change lambda, suppose lambda increases, then K0 decreases, because K0 is nothing but 2 pi by lambda, right. So lambda is in the free space, so this is 2 pi by lambda. So as lambda increases, wavelength increases, K0 decreases, or lambda decreases, K0 increases. What happens to the corresponding value of beta? Beta will also change. Okay. So there exists actually a certain value which is required when you solve that equation. There exists a certain value of beta, which beta of course lies in between K0 N2 and K0 N1. It might happen in such a way that the product that you are looking at, J0 of UA, right. So this product has to increase, because U is now changing. U is changing because K1 is changing, beta is changing. Of course, because lambda is changing, K2 is also changing, as well as K2 is also changing, as well as W is also changing. So essentially U and W both are changing with all the other fiber parameters fixed, except that lambda is varying. It might so happen that the product UA, or the equivalently the value of beta that you find out from solving the equations, might turn up in this region. Okay. If it falls below K0 N2 after you have found beta, then this particular mode does not propagate, which means that the electric field will be 0 here, magnetic field will be equal to 0 here. Of course, it is not exactly 0, because I am looking at guided modes, there will be some evanescent modes and there would be some radiation modes in the cladding, but for the core region there will not be any excitation. Okay. Similarly, it might so happen that as you change lambda, right, so the value of beta that you obtain from solving these equations might increase in such a way that you may end up in this region. In that region again you will see that there will not be any mode which is propagating inside the core. Now suppose by some luck or by some design you are sat in this particular position for a given lambda, okay, which means there is a corresponding beta that is associated for that one, okay, and there is a corresponding nu, the order nu that also you have found out. For nu equal to something you have found out this particular condition. Now remember, for every nu when you solve that equation, you can go back to T0m equation. Here for every nu that you consider, in this case of course nu is given, nu is equal to 0, but the solution of this equation has m roots, correct. The solution has m roots, and corresponding to these m roots of the equation, the value of propagation constant will also be different. Suppose this is the case with nu equal to 0 and m equal to 1, then corresponding to nu equal to 0, m equal to 2, the value of beta might go to this one, okay, value of beta might be here. The second solution which corresponds to this is m equal to 1, this is m equal to 2, or rather the third solution that you are going to look at might end up here. Then it might also happen that one of these solutions which we have written outside might actually be the solution m equal to some number n, but this mode does not propagate. Okay. So that mode does not propagate. Now let us go back and then look at the modes that we have. We have TE0m, TM0m, EH and HE, both are nu times m. Nu can of course be equal to 1 here, and nu is not equal to 0, because when nu is equal to 0 you get these two modes. Now let us ask this question, what is the lowest order mode that is propagating? By lowest order mode what we mean is that you start with k0n2 and k0n1 as the range of the values of beta for which the mode can propagate. The lowest order one is the one which actually starts off by just being, as soon as you start increasing certain values, the lowest order mode will be the one which has this largest value of k0n1, okay. So the lowest order mode starts at this point. Whichever mode that satisfies, that just has value of beta slightly less than k0n1, then it begins to propagate, okay. The next mode that will propagate with a different values of nu and m combination will be called as the first higher order mode, okay. So this is the lowest or the dominant mode, which means this mode exists right as soon as the mode conditions exist, okay. If you go to the rectangular waveguide situation, and you might remember something like this, your frequency f is increasing, right, and at certain particular point you cross what is called as the cutoff frequency. So the mode which has the lowest cutoff frequency is called as the dominant mode or the fundamental mode, okay. For the optical fiber I am drawing it in this way because I am writing this in terms of lambda rather than frequency. So you get this as the lowest order mode or the dominant mode, and then you keep doing this one. Now when you look at the type of modes over here, you might think that the lowest order mode should be the one where m is equal to 0, but unfortunately when you calculate the amplitudes for this case with nu equal to 0 and m equal to 0, the field will not exist, okay. So there will not be any field that would exist at this particular mode, and similarly TM00 mode also does not exist, okay. So you might think, oh well, maybe m is not 0 but m is equal to 1 can exist, that is, can TE01 mode and TM01 mode be the fundamental mode? Turns out that no. Why is because if you solve the equations for solve that big equation and find out the cutoff frequencies or rather the cutoff conditions for each mode, you will see that with nu equal to 0, okay, TE0m mode and TM0m modes that you are going to get will cut off when J0 UA is equal to 0, okay. So when J0 UA is equal to 0, and when nu is equal to 1, the cutoff frequency for HE1m and EH1m modes will begin with will be obtained when you solve this equation, which is J1 UA equal to 0. When nu is equal to 2, you get HE2m and EH2m, and of course with nu greater than 2 you will get similar equations over here. The root for this equation is slightly complicated. This is given in the textbook, so let me not write this particular case. Okay. So for nu equal to 2 and nu equal to 3, the equation is little complex. You can look at the textbook for the expression. But what you have to understand here is that, look at the values of u. Okay. When nu is equal to 1, the cutoff condition is J1 UA equal to 0, and where will this J1 UA equal to 0 will go to its first 0? Right when UA is equal to 0, because the J1 function as a function of the argument UA goes like this, right. So this is the J1 function. J0 on the other hand would go like this, right. So the cutoff condition that you are looking for, you have to at least get to this condition so that the corresponding mode can propagate. Okay. So that happens at the earliest for the HE11 mode, whereas that happens at a later stage, that happens at a later stage here for TE01 and for TM01 modes, right. So for TE01 and TM01 modes, the cutoff condition is that their corresponding value of UA must exceed, or the parameter UA must exceed here. It is the point where so it is this one. Okay. Sorry, this one should be the case where you get TE01 and TM01 equal to 0, and this happens at a value of 2.405. Okay. So when your product u into A exceeds 2.405, or we will actually define a different parameter, but then when this exceeds the value of 2.405, then these two modes begin to propagate. Below 2.405, right, from 0 to 2.405, the equation that we have written has only one solution, which will be for nu equal to 1, m equal to 1, and the corresponding solution is the so called fundamental mode, which is HE11. So you see that this is the HE11 mode, right, which actually begins to propagate as soon as you launch some light into it. So this is the so called dominant mode. Actually we define another quantity which we call as the V number, which tells you how tightly this particular mode is propagating. Okay. It tells you the values of V that is required for a particular mode to begin propagating, and then it will also tell you how nicely confined this mode is into the core depending on this particular parameter. This is called as the V number, and you can obtain V number by starting with this equation u square plus w square, which is equal to k0 square n1 square minus n2 square, this is actually k1 square minus k2 square, multiply by a square on both sides. Okay. So you get a square, and then call this equation or this expression as V square, so that you get V is equal to k0 a square root of n1 square minus n2 square, but I know that this square root of n1 square minus n2 square is nothing but the numerical aperture. So I can write this as k0 a into numerical aperture. Okay. As before, if I fix a, if I fix numerical aperture and fix lambda, then for that particular lambda V has to be less than 2.405, so that only HE11 propagates. When you satisfy this condition, then we say that the fiber is single moded for this particular wavelength. Okay. If you can't satisfy this condition, then the fiber becomes multi-mode. Now it is interesting, suppose I give you a single mode fiber, a standard single mode fiber that I will give you, which has A of 4.1 micron, which has a delta, which is the refractive index difference, right, of about 0.4%. I will say that lambda is 1064 to 1600 nanometer. I want a single mode condition over this entire band of wavelengths. So I want a single mode condition over here. Now clearly if I want to satisfy the single mode condition, at this wavelength my V number has to be less than 2.405, and at this wavelength also my V number has to be less than 2.405. But go back to the expression for the V number. V is inversely proportional to lambda, because V is directly equal to k0 times something. K0 is 2 pi by lambda. So it is inversely proportional to lambda. V is inversely proportional to lambda. Now if you satisfy the single mode condition at say 1600, and then as you start, so initially you might naively think that, oh, let me satisfy this condition at 1600 nanometer. I will ensure that the V number is less than 2.405, so that it is single moded in this wavelength for the values that of the radius fixed and numerical aperture. Now as you start decreasing this wavelength and reach say 1064 nanometer, what you would see is that V number has actually risen up, because all the other parameters are constant, but your your lambda wavelength has decreased. Since lambda has decreased, V number has gone up. So at some wavelength here, which might say 1300 nanometer, it might so happen that the V number has actually increased, so that beyond this wavelength the fiber has become multi-moded. Okay, it can support higher order modes. What are the higher order modes? These are TE01, TM01, HE21 and so on. So these are the three groups which are the first higher order modes. They have their propagation constants almost equal to each other. Okay. So you need to satisfy, if I am designing over a wide bandwidth the single mode optical fiber, you have to satisfy the single moded condition at the lowest wavelength. Okay. So if you satisfied this at the lowest wavelength, then if you increase the wavelength, no problem, because V is anyway going to decrease. Of course, if you keep increasing the wavelength too much, then V would have dropped very close to 0, right. And then you look at the Bessel function, how it performs. So this is the Bessel function that you are looking at, and if you start decreasing V, you are actually moving towards this point. So you won't really get any propagation. Yes, you will get single moded condition at very high wavelengths, but the corresponding propagation constant value is so small that it won't really propagate at all. So if you want to avoid this condition, then you have to ensure that there is a reasonable value of the propagation constant, and this condition of propagation constant with respect to wavelength is captured by defining a new quantity called as B, and B is the normalized propagation constant. It is defined as beta over k whole square minus, or rather k0 whole square minus n2 square divided by n1 square minus n2 square. Obviously when beta by k0 is equal to n2, there won't be any propagation, because this propagation constant B will be equal to 0. Okay. When beta by k0 is equal to n1, you get propagation constant B is equal to 1, which is the maximum possible value that you can have. Okay. So this value that you are looking at, which will give you the ratio of some refractive indices, this fellow beta over k0 is sometimes called as the effective index. Okay. Sometimes denoted by this bar over it, called as the effective index. And people since 1960s have actually worked on this problem in order to give us the values of this beta by k, okay, between these values of n2 and n1. Okay. You see that if you plot this fellow B, or you plot this beta over k as a function of the normalized frequency V. So this V parameter is called as a normalized frequency V. So you will see that for the fundamental mode, it basically begins like this and stays up this way, reaching the maximum value of n1. Because I have written beta by k, my minimum value is n2 and the maximum value of this one is n1. Okay. So as I keep increasing, I will reach here the maximum value for the fundamental mode, and the fundamental mode begins right at almost at 0. Okay. It will almost begin, 0, or it will actually begin at n2, just above n2 actually. So if I am plotting this, I should be little more careful. I should say just above this. Okay. Just above this. Then the next order mode kicks in after certain values of V, which is 2.405. Okay. So this corresponds to TE01. Closely associated with that is is the next mode, which is TM01, and in between these two and then going through them is your HE21 mode. As I said, all these 3 modes have fairly similar propagation constants. Okay. This mode is the fundamental mode HE11. Now, what should happen? I should get for, so this one is for nu is equal to 1, correct? I got nu equal to 1, m equal to 1. So, I suspect nu must be equal to 1, but m must be equal to 2. That is, I have to get EH12 and HE12 modes, right? And you do get these solutions as the next solutions. Okay. However, they will have a propagation constant that is determined in this fashion. So, this is the HE12 solution, and then you also have the EH12 solution, or rather in fact you do not get EH12 solution, you at this point you start getting EH11 solution. Okay, EH11. EH12 will come even more later than this one. Okay. So, you also have another mode which is actually HE31 mode, which is going in between these two. So, there is HE31. Okay. So, you will see that for a corresponding value of nu equal to 1, you will get additional terms, okay, but these terms do not always come in one sequence that you might imagine, because these sequences are heavily dependent on the solution of that equation. But what you have to note here is that until this 2.405 normalized value of V, you only get a single moded propagation, okay, and this would actually be the maximum value of the single mode propagation constant that you can get, because beyond this, if you increase V number, you want to reach for this propagation constant, but unfortunately you are also going to induce other higher order modes. Okay. So, this is what happens. Now, we will go back and look at a different kind of a mode structure, because what we have done so far is that we have not solved it, but we have used the literature results to understand the modes, but turns out that these modes can be considerably simplified. The picture can be considerably simplified if you were to consider what is called as the weakly guided approximation. What is weakly guided approximation? Well, we have been working with the standard single mode fiber values of delta, which is around 0.4% or 0.1%, right. These are very small values, which means that there is not much of a difference between N1 and N2, or equivalently there is not much of a difference between K1 and K2. So, K1 is almost equal to K2, beta is almost equal to these two values, because the spacing between N1 and N2 is this much, just about 0.1% or 0.4%. So, in this approximation you can go back to the original equation that we wrote here, right. So, we had this big equation that we wrote here. Okay. In this equation you can make some simplifications. You can say that this J nu plus K nu is okay, K1 square is almost equal to K2 square. So, I can remove K1 square here, K2 square here, and that is almost also equal to beta square, correct. So, when delta A is very small, the refractive index difference is very small, K1 square is almost constant. So, this can go out, right, be equal to K2 square, and here I can also remove beta square. So, what I get is only this nu by A square, 1 by u square plus 1 by w square. Of course, here you are left with J nu plus K nu. So, clearly I can eliminate this one as well and then put a square here, and I do not want a square here because I want to find out this J nu plus K nu, right. I want to solve this equation. So, I can remove the square here and then put a square root onto this entire thing. If I put a square root, this 2 which is sitting in the power will go away, and this nu by A will also have a power which is 2, that will also go away, except that I now get two solutions. I get actually plus or minus these values, I get plus or minus these values. So, let me erase all these things around it for you guys to look at the relationship. So, this is the actual equation that you are going to obtain for what are called as the linearly polarized modes. So, these are what are called as the linearly polarized modes, and in this linearly polarized modes you actually write down these modes as LP, J, M, where J is a different integer that I am going to discuss very shortly. And the point about linearly polarized mode is that you no longer have to think of ER and E phi in the transverse plane. Under this linearly polarized condition, which applies only when weakly guided approximation is made, instead of ER and E phi you can actually talk about EX and EY. Similarly, you can talk about HX and HY. Now you can talk about X polarized mode, Y polarized mode, or in general an X plus Y polarized mode, that is x hat plus y hat polarized mode. So, this is what is called as a linearly polarized mode, okay, as opposed to ER and E phi, which would have turned around the electric fields. You just get a linearly polarized mode only under the approximation of the weakly guided condition. The refractive index difference must be very small. Now, how do we build up to this equation? The clue comes from this B versus or beta by k versus V diagram here, right. So, you look at these equations over here, you see that there are certain components which are grouped together. There is TE01, TM01 and HE21. What is nu for TE01, TM01? Nu is equal to 0. But look at the second index here. The first index is always equal to 0 here, because for TE and TM modes you can only have solution when nu is equal to 0. Okay. So, since the first index is always equal to 0, I can write down a new parameter called j, which I will define it as 1 for TE and TM modes. You see that TE01 and TM01 are actually having 0 all the time, okay, but then I am defining that as j equal to 1. Okay. So, this is just a fact of definition, but unfortunately this is what we have been following in the literature. So, I am going to follow that. Next, what are the other modes that are paired up here? You can actually see that I have not, maybe I have shown here, you can see that HE31 is paired up with EH11. Now, look at the second index here. The second index for both of them is 1 and 1, but what about the first index? The first index for HE is 3, right. Nu is equal to 3 here, nu is equal to 1 here. If I define j as nu minus 1 for HE modes and nu plus 1 for EH modes, did I get it correctly? So, I think HE31 is related to EH11, then you have HE41 related to EH21, which I am of course not showing in this particular case, but if you consider j equal to nu minus 1 and substitute nu equal to 2 here, you get HE 2 minus 1 is 1. So, you get HE1 1 and then you get 2 plus 1, which is 3. So, you get 3 plus 1. So, maybe I should switch around the way in which I am writing this, right. So, I might have to switch around and then say nu minus 1 for HE modes and nu plus 1 for EH modes. Would that then make sense? So, now I have HE12 here and EH11 here. What I am looking at is the connection between HE31 and EH11. So, let me not write nu equal to 3 here, although that is nu, but if I consider the coupling and then say HE nu plus 1 comma 1 or rather 1 and EH nu minus 1 and 1, if I couple these two modes and set nu equal to 2, I get HE 2 plus 1 1 and EH 2 minus 1 and 1. HE 2 plus 1 is nothing but HE 3 1 and this is nothing but EH 1 1. So, these are the ones which are coupled. Okay. So, I am looking at coupling of HE nu plus 1 and EH nu minus 1. So, these are the ones which I am looking at coupling, and I have defined a new parameter j which would actually reflect this particular condition. Okay. So, my modes are going to be written as LPJM modes. Although we are writing this as LPJM modes, well, I mean we are writing this as LPJM modes, you can actually think of, or rather they are the result of combination of TE0M, TM0M, HE nu m, or rather nu plus 1 m and EH nu minus 1 m modes. Okay. In general, if you take these different modes and for a good measure also throw in HE 2 m. Okay. So, if you put them together, right, and then combine them, then you will end up with the LPJM modes. For example, the fundamental mode in this particular case becomes LP01 mode, okay, and this LP01 mode is actually derived from HE11 mode. In fact, LP01 is very nearly equal to HE11 mode. Okay. The next mode that you are going to get is LP1M mode, and this is coming from combination of TE0M, TM0M and HE2M modes. Remember, in this equation you had, or in this curve you had TE01, TM01 and HE2 1. So, if you combine these 3 different modes, you will end up with LP11 mode, because LP1M mode is the combination of these 3 type of modes. So, you end up with LP11 mode. Then if you combine this HE31 and EH11 type of modes together, okay, then you will get the modes LP nu M, where nu is greater than or equal to 2. Okay. This comes from combining HE nu plus 1 M and EH nu minus 1 and M. The fundamental is of course LP01 mode, which will always propagate. And what is the nature of the LP01 mode along the radial direction? It would be J0UR, right. You sketch this J0UR as a function of R with respect to A here. So, you see that this should be a Bessel function like this, right, and then at R equal to A and R equal to minus A. Minus A is simply phi equal to 180 degrees, so just going in this particular direction, right. So, you will see within this core your electric field patterns are maximum at the center. So, you get a maximum electric field at the center. So, you can actually close an optical fiber over here. Okay. So, you can close an optical fiber over here with the core, and you will see that the electric field lines are actually maximum at the center of the field, and they would decay as you go away from the radial direction. But this is the value of the HE11 or the LP01 mode at the core. Beyond this, of course, you actually expect the fields to basically decay. In the same situation that I have considered, you can see that instead of talking about this Bessel function mode, which is slightly difficult to handle mathematically, there is an actually nice approximation of this mode as a Gaussian mode. Okay. So, as a Gaussian mode, there is a nice approximation to this J0 or the Bessel function mode. You can actually check that one by writing a simple code in MATLAB. Plot J0 square of x over, say, x is from 0 to 2.405, and similarly plot Gaussian function, which is e to the power minus alpha x square x square by a square. Okay. So, this would be J0 square x by a. So, if you plot this 2 and then you can adjust the amplitude, so you will be able to approximate a Bessel function by a Gaussian function. Okay. And you can see here that this Gaussian approximation actually goes slightly beyond your core, right. The mode actually is not going to 0 there, it is going slightly after the core as well. So, this particular diameter, after you obtain this particular diameter within which 90% or 99% of the energy is concentrated, is called as the mode field diameter. In fact, it is this mode field diameter which is very important when you are coupling light from a light source into the fiber. Okay. So, this is abbreviated as MFD. There are nice expressions for MFD in terms of the V number, in terms of some fitting parameter, namely the mode field diameter fitting parameters. You can look at those expressions in the textbook. Okay. So, this will simply tell you that for a given radius A and for a given value of V, how is the width, which is denoted by W0, just to confuse you, how is the width or the half of the mode field parameter, so that the power is concentrated about 99% within this mode field parameter is there. So, W0 by A is some function of V and some fitting parameters. This is not theory for this one, there is just a fitting parameters that is obtained from experimentally measuring the mode field. Okay. So, this is what the lowest order mode and its mode field diameter is. It turns out, however, that you will actually get 2 types of modes here. You will get LP01x and LP10y, that is, one of the fields is directed along x axis, the other field is directed along the y axis. Both have the same value of beta. Okay. So, one of them is called as the horizontal mode and the other one is called as the vertical mode. Here the field lines here would be in this way, the field lines for the vertical mode would be in this way. Of course, they would actually have to curve a little bit as you go out, but here again they have to curve a little bit as you go out, but this is the horizontally or the linearly polarized mode here within the core LP01, and the other one is the vertically polarized mode. Although in a nice fiber this value are the same, in practice these values start to change slightly as you begin to propagate inside the fiber. As you keep traveling along the fiber, these values change slightly, leading to a dispersion or a delay between these two modes. So, LP01 arrives slightly ahead of LP10 mode, like that. So, there is a small dispersion, and this is called as polarization mode dispersion. This polarization mode dispersion is a notorious quantity. It is not characterized by any proper theory. There is a lot of statistical analysis one has to do in order to characterize this polarization mode dispersion, which is one of the main limiting factors in high speed optical communication links, okay, especially important at 10 gigabits per second and 40 gigabits per second. So, we will close our discussion of optical modes here. You may have to look at some assignment problems to understand more properties about that, and we will begin with study of pulse propagation inside an optical fiber in the next module. Thank you very much.